VDD volts 1.
I mean, this is my first.
EN 5 volts. EN okay, so calculate IDQ VESQ. A, so V is by input resistance, output resistance. Okay. Maybe we do the low lines also. Okay. So this is IDQ, correct? We have VDSQ, and I'm going to call this as V sub G, correct? Voltage here as V sub G. So basically, V sub G is the voltage across here, right? Right? So V sub G, according to the voltage divider rule, yes? Okay, and that will be about equal to 9 volts. Right? Then we go around the loop. E sub G equal to VGSQ plus IDQ R sub S. Right? So you have one equation and two unknowns, right? This is not known, this is not known. So you need one more equation. So now if you assume situation, right, then IDQ formula is VGSQ minus VGN to the square, right? Okay, so you put this equation here, right? You would have one unknown, right? So therefore, you can calculate VGSQ, and it's about 2.9 volts. And therefore, you can calculate IDQ. It's about 8 milliamp. Okay, now we can go to the output loop, right? Output loop. So VDD equal to VDSQ plus IDQ R sub S, right? So therefore, VDSQ equal to VDD 12 minus IDQ, which is 8 milliamp times R sub S, 0.75. So what did you get? 8 times 0.75, huh? About 3.9? Not sure. Yeah? So anyway, let's say it's about 4, right? So that's 8 volts. It's correct now. Huh? It's around 6?
Yes.
Yeah. 6. Okay. So you get 6 terms, right? So basically with this and that, you have found the what? The Q point. Yes? Okay, now we have to verify this assumption. Yeah? So the question is VPSQ larger than or equal to VP set? Yes? So what's VP set? VP set is equal to VGSQ minus VPN, right? So that's 2.9 minus what? 1.5. So this is 1.41. So this is 1.4. This is 6. So the assumption is checked. Yes? Okay. Then we can go to the AC analysis, right? So from the left, you have V sub I, right? And then capacitor is a short circuit for now. And then you have R1 in parallel with R2, right? And then it's connected to the gate of the MOSFET. Okay, and the source is connected to R sub S to the ground, yes? And then the drain is grounded. Drain is grounded, correct? Okay, now I'm going to fill in the model. Yes? This is VGS. This is GM VGS. That's R sub O, right? You cannot neglect R sub O this time because lambda. Yeah? Lambda is given. Okay. So let me see what is G sub n. Huh? G sub n, the formula is 2 is equal to 2kn VGSQ minus VPN, right? So 11.3 milliamp per volt. Okay, R sub O is 1 over lambda IDQ. Okay, that's the formula I gave you earlier. And lambda is 0.01, right? IDQ is known, correct? 8 milliamp. So therefore, I get 12.5K. Oh, yeah. So far so good. Huh? Now, I think it's better to redraw this because it's kind of awkward, right? So let me redraw this. That will help you better. Okay, let me see. So this is the source, right? So the source is grounded. The source is going to R sub S and ground, right? And then the drain is grounded. So I can put the drain here, can I? And then basically I flip this downward. Yeah, got it? So therefore the current actually is going what? Going up. then R sub O. Yes? Agree? Huh? GM BGS, right? So this is BGS. Can you see that?
It just makes it easier to like work with.
Yeah.
Okay.
I think it's easy. This is V sub I, R1 imperial with R2. Yes? Agree? Okay, where's V sub O, by the way? Oh, I did not tell you, huh? V sub O is taken from here, okay? So that's V sub O. So therefore, V sub O is somewhere here, huh? V sub O. Yes? Correct? Okay. Once you have that circuit done, you just have to go through the circuit analysis, right, and some algebra. All right. So this is V sub O, correct? So what's that? So basically, this and that are in parallel. Yes. Okay, and the current going up, so basically you can put this in two in parallel. The current is going downward. Huh? So V sub O is GM BGS times R sub S in parallel with R sub O. Correct? Okay, then what's V sub I? And the key is that you want both equations to be functions of BGS, right? Okay? So V sub I is here, right? So that is also V sub I, right? Same. And now BGS is here. So how do you correlate BGS with V sub I? Can you go this loop? Can you go this loop? Yes? So, if you consider loop, what is V sub I? BGS plus V sub 0, right? Agree? It's the same. V out here or V out here. Same. So you can go, the loop can come here as well. Doesn't matter. Huh? So this voltage is this plus that. Good? And that, what is that? That's V sub O. Yes? So it's equal to VGS plus V sub O is here, right? So it's GM VGS times R sub S parallel with R sub O. Right, then you just take the ratio, right? So you will get GM R sub S in parallel with R sub O on top, right? And then 1 plus GM R sub S in parallel with R sub O on bottom. You should note that for this type of amplifier, A sub B is always less than 1, okay? For the common drain, the voltage gain is always less than 1. For the common source, the gain is always larger than 1. Is it correct? Less than 1? Yes? Because you can see that the denominator is always larger than the numerator, right? Okay. Any more questions about this? Okay, then let's try to find A sub I. So let's say this is I sub O, right? No, I sub O actually is going from where? It's not from there. It's from the R sub S, correct? Because that's the that is considered the load of the output. Huh? So basically, I want to find out what is I sub O, which is current going to R sub S. Huh? Then you can see that you have two branches. Yes. So you can use the current divider rule. So the main current is GM VGS, correct? And then you get divided by the two branches. So R sub S plus R sub O, then R sub O on top, right? And then the input current. So this is the input current, right? I sub I. So this current, is this current the same as this current? Huh? Is it the same? It's only one loop, right? Okay. And that current, what is the voltage across here? Huh? VI, right? Okay, so I sub I is V sub I over R1 in parallel with R2, correct? Okay, and V sub I is already derived, right? So it's VGS plus GM VGS RS in parallel with RO, right? Divided by R1 in parallel with R2. Yes? So now I can divide the two. So A sub I now is equal to, this is on the top, right? So it's GM R sub O plus R sub S, right? Then this is on the bottom. So that's R1 in parallel with R2. 1 plus GM RS in parallel with R sub O. Alright? By the way, I should have some numbers, I hope. So this number I got right here, huh? For A sub B, I got about 0.9. Okay, and for A sub I, according to my notes, which is not always accurate, I got 197. Okay, then let's try to find out what is this. Let's try to find out what is the input resistance and what is output resistance. Huh? So what is Rin, which is called the input resistance? What is the definition? Huh? Is V I over II, correct? Well, simple, huh? Simple, isn't it? Well, because this is not connected If this were connected, it's a different story, huh? It's not connected, so you have a single loop. So what is R sub in? Which is R1 in parallel with R2, correct? Okay. Then let's try to find out what is R out. R out, which is called output resistance. Well, to do this one, you have to use the Thevenin equivalent circuit. Okay. So basically, you have to put a test voltage at the output. And then when you do the test voltage, this one will become a short. Yeah? So that becomes a short. R1 in parallel with R2. Right? G S R sub S. Then you put these two together, make it easier to see. Right? Right? RS, RO, that's the current source. Alright, then basically that is the resistance you're looking for, right? So this is called R out, right? Okay, to do that, the best way is to put a test voltage, V test, right? And then the test voltage will generate I test. Yes? So therefore, R out will be V test over I test. Right? Sometimes we want to assign a number to V test to make it easy. Huh? You can assign any number. Yeah, but you want to choose the simple number, right? You don't want to choose a complex number. So I can say V test equals 1, right? Make it simple. Okay. So now, this is 1 volt. The question is, what is I test? This is a node, correct? So I test, according to KCL, yes? 1 equal to what? 1 over R sub S plus 1 over R sub O, right? Why? Because this is 1 volt, right? 1 volt. So there's a current here, there's a current here, and this current is entering, right? So it should be what? Minus GM VGS. All I did was I used the KCL, yes, for the node, that's all. It's nothing tricky. Okay, but what is VGS? Because this is unknown. This is VGS, correct? VGS. Now look, VGS, the negative polarity is attached to the plus of VTest, and the positive is attached to the minus of VTest. So what does that mean? So VGS is minus VTest. So minus 1, correct? You see that? This node is the same as this node. Got it? This node is the same as that node. But the polarities are opposite. That's why I have to put a minus sign. Okay. Okay, then you put it here. So it's what am I looking for? I'm looking for I test, right? So why am I doing this? Huh? You guys told me I made a mistake, right? So this is I test, correct? Equal to that plus that, yeah? Should be I test, it's not 1, okay? So now I can put this in here. So I test equal to 1 over Rs plus 1 over RZL plus, right? Because GM. Okay, then as I said, RL equal to V test, which is 1 over I test. Yes? So it's equal to 1 over 1 over Rs plus 1 over R0 plus GCN. Got it? So that's the solution. If you want to do the low line, it's quite simple, right? Because if you look at the output loop, VTD equal to VTS plus IPRS, right? Okay, so based on that, the low line is simply this is VTD, this is VTD over what? Huh? RDC is RS, correct? Okay, so the Q point, anyway, somewhere, okay? You can look at the Q point. Okay. And then you have the T point, right? So there's IDQ, there's a VDSQ. So for the T point, how do you find the T point? You use the same equation, right? And then you put VDS as VDST, or an ID as IDT, yeah? R stress. And then you have the second equation, which is IDT. IDT equal to what? KNVDST squared, right? So that's the two equations you can use to calculate the find the T point. So that is the whole picture of the DC low line. Now you need to find the AC low line, right? So if you look at the circuit, well, there's no capacitor, right? So you should know that the AC low line is overlapping, right? The DC low line, correct? There's no difference. Okay, so based on that, you can figure out what is your I sub D, maximum I sub D swing, correct? Maximum I sub D swing. What is it? The upper bound is here, right? The lower bound is here. The Q point is here. So you have two windows, right? The smaller window is the maximum I sub D swing. Huh? And then if you want to find the maximum B sub O swing, what is it? Then it's maximum I sub D swing times what? You have to come here and look at the circuit, right? It's the I sub D times what? The parallel of the two, right? So the maximum BO swing the maximum B sub O swing is equal to the maximum I sub D swing times R sub S imperial is R sub O. Okay? So basically in the lab, right, if you have a circuit like this, yeah.
For R out, it's G7 is in kilo ohms, right? And then RS and
Yeah, it should be ohm. Right. This is 1 over, this become mu, right? Mu. But 1 over that becomes, this is in mu, right?
Oh, okay.
Yeah. This is not ohm. So basically, you have a circuit like this, right? How do you correlate the measurement from what I have shown here? So you have an input source, right? You can increase the input source, and you can look at the waveform and the output. Yes. Okay. You can increase until you started to see the distortion. That is the moment of the maximum output voltage rate. Then you can ask me, what is the maximum V sub I can have before distortion? How do you find that? Then, yeah, so the maximum V sub I is equal to what? It is the maximum V sub L swing divided by what? A sub B, right? So that's the maximum input you can keep to the circuit before, without any distortion. All right, so I have finished this example. Now, I would like to modify it a little bit, because sometimes you may see a circuit that has an R sub S, okay? So now I'm going to try to tell you how to do this kind of problem. Okay, so I'm going to use the red color, right, because I have modified the circuit. Now, the DC analysis has no change, correct? Because when under the DC condition, this is open, so that doesn't matter, okay? For the AC condition, the circuit becomes R sub S, right? And then the rest of the circuit is the same, correct? Yes. Yes? Or if you compare this and that, right? All I did was I have added R sub S, right? So this is V sub I. All right. So V sub O, what is it? It's a current, right? So two parallel, so it's the same. Gm VGS times R sub S in parallel with R sub O. Right? No change. What about V sub I? V sub I now is equal to what? I'm going to call this V sub prime, can I? V sub prime plus VGS plus V sub O. Yes? In the first example, V sub prime was 0. Yeah? Because there was no resistance. Right? It's just VGS plus V sub O. But now we have V sub prime. So what is V sub prime? There's a current, right? I sub I, correct? The same current, huh? Same current. And I sub I is equal to what is the voltage across here, by the way? Huh? What's the voltage? Is it VGS plus V sub O? Is it? voltage cross here is VGS plus V sub O, right?
Yeah.
Okay, so I sub I is VGS plus V sub O divided by what? R1 in parallel with R2. Right? Because that voltage divided by that is the current. Huh? So therefore, if you put here, is equal to V sub prime is what? Is I sub I R sub S, yes? Plus VGS plus V sub O. So that's V sub I. Yes? From here to here. And I sub I is here. Now I'm done. Why? This is a function of VGS. This is a function of VGS. Because, well, there's a V sub O, but V sub O is a function of VGS. So all you have to do is just some algebra, right? Can you do that? You should go home and try it. But the concept is more important, huh? Okay. What about A sub I? A sub I will be similar, right? So basically, I sub out is equal to GM VGS times RS plus RO, right? That's the current going through here, which is I sub O. All I did was I used the current divided by the rule, yes? And then I sub I, oh, it's given here already, right? So I sub I is VGS plus V sub O over R1 in parallel with R2, right? And then V sub O, as you know, V sub O is here, right? So it's a VGS plus GM VGS RO in parallel with R sub S, right? Divided by R1 in parallel with R2. Now I'm done. Why? Both equations are a function of VGS. Huh? So you can derive the expression of E base of I. Right? Yeah.
So the input resistance, would that just be Vn over R1 parallel R2 plus Rs?
What did you?
With the input resistance this time?
Oh, the input resistance? The input resistance now will be that plus that. Yeah, yeah. That's it. Okay. So with the same circuit, I would like to do a design problem. Okay, design. So it's the same circuit, okay? Same circuit. And no RS, okay? So maybe I should go back to the black color. Okay. So with the same circuit, I have R1 plus R2 equal to 140K, Kn equal to 1 milliamp rho square, Vpn equal to 0.8 volts, lambda equal to 0.015 volt minus 1. So it's a different circuit, different problem now, okay? Now, we want to design the circuit so that IDQ equal to 1.5 milliamp, VPSQ equal to 5 volts. Yes? So what what am I looking for? Huh?
Pretty much that's the R1.
Yeah. So you need the values of R1, R2, and RS, right?
Which RS is equal to 0, the input one or the source?
Oh, yeah. Got two RS, huh? So I'm talking about this R. I call this RS prime, huh?
Alright.
So it's RS prime. Okay.
Thank you.
Okay. So now you should know, because of that information, we should be able to find something. Okay. So if you go to the output loop, right? So VDD equal to VDSQ plus IDQ RS, right? Very simple, huh? This is known, correct? Huh? What's VDD? Must be known. Okay, VDD is equal to 1.21. VDD equal to 10 volts. Okay. Okay. So this is known. This is known. This is known. Huh? So there's only one unknown, which is RS. So RS is equal to 3.3 KO. All right. Now let's try to figure out what are the values of R1 and R2, right? Okay, so I know that this equation like dq, right? Kn VGSQ minus VTN squared. We cannot solve it, right? Because we do not know what's VGSQ. Oh, no, we can solve it. We can solve for VGSQ, yes? Okay, so I can solve for VGSQ because this is no, right? Okay, so what is VGSQ? VGSQ is 2 volts. Yes? All right. Then I know VG equal to VGSQ plus IDQRS, correct? Huh? If you look at the input loop, yes? Yeah. Okay. So from here, this is known, this is known, this is known, right? So therefore, VG is equal to 7 volts. Right? Okay, then there's a formula. VG is VDD times R1 plus R2 and R2, yes? So now, known is known, known, this is known, yes? Fortunately. Correct? So therefore, you can find R2. And I got R2 equal to 280K ohm. And then once you know R2, you know R1, huh? So R1 is about 119K ohm. So that's a design what?
You add those, they don't equal to 140K though.
Huh?
The sum of those two is not 140.
Oh. Okay.
Yeah,
280, 119. What was the sum? 140. Oh.
I got RQ with 98.
98. Oh, good. 98, so I made a mistake. 98K, so this one must be 140 minus 98, right? So that's whatever. Okay, I hope I have time to do one more example. I think I should have. Good. So let me summarize what we have done so far, right? So we have done examples for the common source. We have done example for the common emitter. So now it's time to move on to the multiple stage. Yeah, multiple stage. Okay. There are two types of multiple stage MOSFET amplifiers we have used commonly. One's called the Casco, okay, one on top of the other. The other one's called a Cascade. That's one after another. Okay. So today I would like to do a Casco, one on top of the other. And next time I will do the Cascade. Yeah. Good. Okay, so let's do case code. Amplifier. Okay. I'm not going to use any numbers. I will just give you the expressions. Okay. So now you can see, I think we did something similar, right? In the previous chapter, when we were talking about the DC biasing. Remember? Okay. This is a very commonly used circuit, which has a load, right? For the load, the gate is always connected to the drain, and then you have a driver, okay? Okay, so here, let's try to find out what is IDL, IDD. L means load, D means driver, yes? We'll find out what is A sub B, what is A sub I, yes? Let me see what else I will find. Let's try to find out what is R sub in, R sub out, the low lines. So we find everything. I hope I have enough time, okay? Okay. First of all, you should know that as we talked about last time when we did the circuit, whenever you have a gate connected to the drain, this is in saturation, right? So the low is in saturation. So you don't have to verify the assumption. Okay. First of all, you should know that IDL is the same as IDD, right? Oh, where's V sub O, huh? V sub O is taken from here. So that's V sub O. Because there's nothing connected to the terminal here, this is open, right? So the current here must be the same as current here. Okay? And VGSD is the same as VGS. Under the DC condition, this is a short. Got it? I did not put a capacitor. If I put a capacitor, then this will be open. But if you put a capacitor, this is not going to work. Got it? If you put a capacitor, there's no DC bias to the circuit. It's not going to work. So this is in the DC condition. This is short, right? So this voltage is the same as that voltage, right? So VGS the same as VGSD, yes? Okay, which is known, by the way, it should be given, huh? So this is given, okay? All right, then IDD is equal to KND VGSD minus VTND to the square. Okay, if you assume saturation, huh? For the driver. So this is the drain current for the driver, right? That is the threshold voltage for the driver. Known, right? Right here, known, because these are parameters that's supposed to be given. So therefore, IDD is known. You can calculate. And therefore, this is IDL. Okay, then I want to find out what is the DC voltage at the output terminal. Then, if you look at this equation, look at the circuit, that is VDD minus VDS low, correct? This voltage to ground is that voltage minus that voltage, yes? That's VDSL low. But VDSL low, if you look at the circuit, you should know that is the same as VGS low, right? This voltage is the same as that voltage, got it? Because the gate is connected to the drain. Okay. Then what is VGS low? Well, since I know what is VD low, which is Kn VGS low minus VTN low to the square, right? It's known. Why is it known? Huh? Because here. Because IDD is known. IDD is the same as IDL, so it's known. So this is known, known, known. So therefore you can find out what is VGSL. So this will become known. And then you put it here, right? Then V sub O becomes known. I know it's a little bit confusing without the numbers, huh? Maybe not. Okay, so let's do AC analysis. Okay, let's do AC, which is a lot trickier. So I hope you're not like my son who got scared by all this stuff, huh? You like it? All right, so let's do the AC. So you always start from the V sub I, right? Okay. So you go from V sub I, and under the AC condition, this is short. Yes? Okay. So you have V sub I on the left hand side. That should be no problem, right? Okay. Then You have to watch out, okay? Then it is connected to the gates of the driver. Yes? And then the source is grounded. Right? And then the drain is the drain of the driver. The drain of the driver is connected to the source of the load, right? Agree? Okay? And then the drain of the load is connected to the ground. Agree? And so is the gate of the load. Yeah? Because the two are connected. Okay. And then this is actually our V sub O, right? If you look at the circuit. Okay. Now that is the model for the driver. Drain to source, right? So it's GM driver, VGS driver. So this is a VGS driver, right? Correct? Okay. Now, for the load, the driver actually, the drain is actually on the bottom, the source is on the top. So that means the model will have to be flipped. Got it? Because the current source always go from the drain to the source, right? So therefore, for this part, which is the load, since the drain is on the bottom, the source is on top, so the current will go from where? Go from bottom up, right? So this is our G sub M load, VGS load. Yes? Now, where is VGS load? Well, it's here, right? VG, right? Load, S load. So VGS load. Why am I putting plus here, minus here? Because VGS, right? G to S.
So it would just be the opposite of the
Yep, that's correct. Now this is, I have to say, this is a little tricky, yeah? But you must know how to do this. Now if I put a capacitor and then a load to the ground, then what is it? If I put a capacitor and a load, then I will simply have to what? Put the R sub L here, right? Correct? Huh? Because you go from the source to the ground. Yeah? Okay. So that's what it is. Alright. First of all, you know VO is equal to minus VGSL. Yes? and the VI is what? VGSD, right? Agree? And then, look here. It's a single loop, right? So these two currents must be the same, right? This one goes down, this one goes up, but it doesn't matter. The two currents must be the same. So therefore, GMD VGSD must be the same as GML VGSL. Yes? So therefore, VGSD can be expressed in terms of VGSL. Yes? Now I'm going to put this here, right? So V sub I, which is the same as VGSD, is GML, GMD, VGSL, correct? And now I can take the ratio. So A sub V will become -1 GML GMD. So it's equal to minus GMD GML. So basically, for this type of amplifier, the voltage gain is always the ratio of the two transconductors. Any questions before I move on? I think the key is really to construct this circuit. Okay, if you know how to construct this circuit, I think the algebra is not so bad. Something to think about, okay, when you go home. Okay, now what about A sub I? Well, A sub I, we don't have a load, right? So it's hard to figure out what's the output current, right? So let's say you have a load here, okay? Then what is the low current? Huh? What do you think? The current is a known, right? So this current is the difference of these two currents, correct? You have a current here, you have a current here, right? So this current is the difference of these two. That's it. Yeah.
But there's no difference, right?
Well, without that, these two currents are the same. Huh? But with that, it'll be different. I don't want to confuse you. So let's say we don't have R sub L. Okay? So therefore, without R sub L, I cannot find A sub I, okay, because it is it's irrelevant. All right, so let's move on. What about R sub I? R sub in by definition is what? Is V sub I over I sub I, yes? What is I sub I? Yeah? It's not 0, it's infinity. Oh, I'm sorry, it's 0, yeah. So this is 0 because it's open circuit, right? So therefore, yeah, R sub is infinity. Yeah. Okay? Because this is 0. Oh, okay. So what about R sub out? R sub out would be like this. Now I have to put a test voltage. voltage, yes. So I'm going to put a test voltage, V test equal to 1 volt, right? So this becomes I test, yes? GMV, GSD, GMV, GSL, right? So this is VGSD, and this is VGSL. Yes? Everything is the same, huh? Except that I have disabled this I, make it short circuit, and I have added the test voltage. Yeah? So, R out is what? Is test voltage divided by I test, correct? Okay, now what is I test? What is I test? I test, if you look at this node, right? There are how many currents? There's a one current, there's a one current, there's the first current, right? So I test is equal to what? I test equal to, which one is leading? Yeah, so it's GMV, GSD, yes? My,
Wait, no.
it's the other way around. L, right? L, GML minus GMVGSD, right? This is L, this is D, by the way, right? There are two different GM, huh?
So the circuit and then 0.
Okay,
Right.
but then we know that VGSL is minus 1 volt, yes? Because this is VGSL and this is 1 volt, right? So this is minus 1 volt. So therefore, you put this in here, right? But what about VGSD?
Equal to VGSL.
Huh? What about VGSD? VGSD is right here, right? What is the voltage? It's 0, right? There's no voltage. This is short, by the way. Yes? So you are talking about voltage across a short. So it's 0. Got it? So VGSD is 0. So therefore, I test is equal to minus GML. So therefore, R out is equal to 1 over I test equal to minus 1 over GML. Huh? Correct? Okay, let's do the low line. The low line also becomes tricky. See how much time I have. Oh, okay, let's do this quickly. If you have to do the low line, you have to use the output voltage, output loop, right? So it's VDD plus VDS low plus VDS driver, right? But how are you going to construct the load line? Huh? Typically, you have an equation that has what? That has the current and that has the resistance, right? Yeah. Well, so what you have to do for this case is that you should consider the load as a resistance, okay? It is a resistance, okay? So let's call R prime, correct? VDD. So then we have ID driver, right? So therefore, VDD equal to ID driver R prime plus VDSD. Yes? Okay, the question is what is R sub prime? Well, R sub prime is equal to VDSL load, right? Divided by IDSL, right? Which is the same as VGSL over IDL. And by the way, this is known, right? We have calculated these two parameters in the DC analysis. So therefore, the resistance associated with the load can be found. Yeah? Okay, so once it's found, then based on this equation, you can construct the DC load line, right? So this is VDD, this is VDD over R prime, right? Correct? Because R prime becomes the DC resistance, and then you put a Q point. So this is ID driver. This is the VDS driver, right? And we know this right away, right? From those. So therefore, the Q point can be found, and then you go ahead and find a P point. The P point is the same equation, right? So VDD equal to ID LT R prime plus VDS DT, right? And then ID LT Kn VDS DT squared. So these two equations allow you to calculate IDLT and the VDS. What is IDL? IDP, right? Yeah. So I think it's right. ID. This is IDP, okay? IDP. We're talking about the driver, okay? The load is represented by R sub prime. So when you're talking about a Q point, it's the Q point of the driver. Huh? Also the P point is the P point of the driver. Okay, I'm out of time, but I think I finished the example. Go home and study this, okay?
Not here.